The other piece of information we like looking at when investigating data is variance. So our random variable that we're investigating, x, this is how we work out the variance. It works out to be the sum of x minus the mean squared times the probability of the thing we're looking at, so the probability of x. And why is that? Remember, px represents probability of x, and the mean is the expected value of x. X minus the mean, basically it's the deviation from the mean. How far away are we? And so this is basically working out is what is the expected value of the score from the mean. The reason we square it is because some of the scores will be above the mean and some of the scores will be below the mean. And if we're trying to find an expected value of that, or an average if you like, you're going to have negative ones and you're going to have positive ones, when really all we're concerned with is the actual distance, not whether it's below it or above it. So for that reason we square it, and then we don't have an issue with the sign because we'll always get something that's positive. So the variation is the expected value of that deviation squared. Let's go back to our milk data here, our family. We now add in another row. These were the two rows we had yesterday. So probability of x, and then we worked out xpx so we could work out the expected value. And remember, the total of that row, that's our expected value or our mean. We now want to work out what is the distance of x from that mean squared. Done that for each of those values. So now I want to get that and multiply it by the probability of x. I have all those. Add them together, I get 1.52, and that is our variance. That's a pain in the neck. So there is a better way of doing it, okay? Because if we play around with our expected value, remember this is the expected value of the deviation squared. So that's what we're saying. Now if I use those laws of expectation, I can simplify this. Because if I expand out x minus mu squared, well I get x squared minus 2 mu x plus mu squared, but we had a law that said we could break those up, in this case to 3 different expected values. So the first one will just be the expected value of x squared. The second one, well I can factorise the constant out of that sum. I'll get 2 mu times the expected value of x. And then the last one is just a constant, mu squared. Well, the expected value of that constant is the constant. But we also said the expected value of x is mu. So now I can make this minus 2 mu squared, giving us a much neater formula. The expected value of x squared minus the mean squared, or a better way of saying it, the expected value of x squared minus the expected value of x squared. Okay, so back to here. There's our table. We can add that up and we get the expected value of x. But now we just need one more row where all I now do is multiply by x again. And I'll get x squared probability of x. Sum that up, that's 6.36, but that's the expected value of x squared. So the variance, expected value of x squared minus expected value of x squared, and we get 1.52. And I think that's a neater way of finding the variance. Because it just involves multiplying by x just one more time. That's all it involves. Which then brings up standard deviation. Well, we've now squared our deviation. And so the units for that are units squared. But if I want to use that to talk about my data, I want it in the same units as the data. And that's what standard deviation is. And all we just do is find the square root of the variance. And that brings it back to the units we want. Or another way of saying that, and we often see this symbol for variance, is just it's the standard deviation squared is variance. So in our example, square root of 1.52, the standard deviation would be 1.23. Standardising data itself, it allows us to compare one set of data to another set of data, and we do it a lot. So let's say our original data is the expected value has an average, mu, and the variance will be the sigma squared. What a lot of non-mathematicians do is they say, has this ever happened? You get results back and the teacher goes, oh, well, look, yeah, thought the marks were a bit low, so I'm just going to add 5 marks onto everyone to boost the marks up. Right? Not a great way of standardising data, because this is what happens. I get this new random variable, which I'll call y, and what I'm saying is I'm just going to add some constant number to every piece of data, so x plus c. So what does the expected value of y become? Well, it's going to be the expected value of x plus c, which I could break up into 2, and as you would expect, the average is just lifted by c, because if you've added c to everything, that's what happens. But what happens to the spread when you do that? It's now the variance of x plus c. Remember, variance is the expected value of it squared minus the average squared. So this would be the expected value of x plus c squared minus the average plus c squared. And again, I could expand out, group things together, and we end up with the variance. It doesn't change. Well, again, think about it. That makes sense. Simply adding a constant amount doesn't change the shape of the data. It just basically shifts the curve. That's all we've really done. So if that was the original data, and we just added c to everything, it's still the same curve. The spread's exactly the same. Haven't achieved much. What if we tried this crazy idea and said, how about we divide every piece of data by an amount? So the expected value of z would now be the expected value of x divided by k, and the variance of z would be the variance of x divided by k. I could factorise the 1 on k out the front of the expected value, and so it becomes the expected value of x on k. My new average would just be mu on k, the variance. X on k. Well, that's going to be the expected value of x on k squared minus mu on k squared, the average squared. But again, in this expected value, the 1 on k squared now I could factorise out, and I'll get the expected value of x squared over k squared minus mu squared over k squared. The top of the fraction has just become the variance of the original data. So we get sigma squared on k squared. So it has changed the shape of the data. Say this was the original one. What have I done? Well, I'm assuming k is bigger than 1. So I've divided mu by a number bigger than 1. It's become smaller. So the mean has shifted. But also the deviation has come in as well. So it changes the actual shape of the curve. So what do we do with z-scores? Because that's what we tend to use when we're comparing data. So what's happening there? There's the formula for creating a z-score. X minus the original average divided by the original standard deviation. So what would be the expected value of z? It becomes the expected value of x minus mu on sigma. Sigma is a constant, that could come out the front. So it's the expected value of x minus mu. That's going to be mu minus mu, because again, I could split that into 2 and say it's the expected value of x minus the expected value of mu. Well, that's a constant, that's going to be mu, but also the expected value of x is mu as well. Bingo. The average becomes 0. The variance. So we will get the variance of x minus mu on sigma becomes, again, on the bottom, remember it's the expected value of that. So I could factorise the 1 minus sigma squared out. I'm left with the variance of x minus mu on top, but the variance of x minus mu would be sigma squared. So sigma squared on sigma squared, which is equal to 1. And that's why when we're looking at our z-scores, we say, okay, one standard deviation from the mean is a z-score of 1, and so on and so on. All right, 13C we can play with.